Edmund Halley, a few years later, would identify a periodic comet and predict its return based on Newton's laws, although probably you could argue that he used Kepler's result more directly. In 1728, and this was posthumously published, basically it was the popularization of Principia Mathematica, there was an interesting graphic called Newton's Cannon, or sometimes called Newton's Cannonball. You can Google either one, where Newton proposed that if you had a tall mountain and a cannon on top of that mountain, according to his law of gravity, as you fire the cannonball with higher and higher velocity, the cannonball will go further and further until pretty soon you start having to deal with the curvature of the Earth. Pretty soon the Earth starts falling away due to its own sphericity as the cannonball moves, as the cannonball falls. And you will reach a point where, of course, you will get an orbit. No one in Newton's day could do this experiment. And you'll find that in a lot, and one of the reasons why I use some of this is in dealing with some crank science claims is they often complain, well, you can't do this experiment. Well, there's a lot of experiments on things that we know today that we could not do for a long time. And that's some of the history of what I'm doing this talk. Around 1763, they got a little bit better estimate of the astronomical unit by Venus transit, or at least they put a lower limit on it. They claim the one, some people argue that Cassini's number was actually an upper limit based on re-examining his measurement. And the modern value is 93 million miles, by the way. So actually, for 1763, they did pretty darn good. Neville Mescaline, around 1774, decided he would try to measure the density of the Earth by measuring the deviation of a plumb bob from vertical near a mountain. Basically, you know, taking this here and seeing, okay, well, if the mountain's over here, the gravity of the mountain should pull it over a little bit, and try to use Newton's law to get an estimate of the density, the gravitational law. And it's called the Schehallien experiment after the mountain that was used for this case. Well, in 1797, Henry Cavendish tried to do a similar experiment using a torsion balance. But he was really interested in the density of the Earth. It turned out that as a byproduct, he managed to get the value of g in Newton's equation, in Newton's law of gravitation. And finally, in 1802, Carl Gauss, in a move that made him a bit of a celebrity, used previous sightings of an asteroid that they had detected just before it was blocked. Our view of it was blocked by the sun. He managed to determine the orbit from previous observations and tell observers where to look to recover this object. And this series became one of the objects in what we today call the Asteroid Belt. They were looking for a planet in this location, but Ceres is one of I think it's actually one of the other ones that they spotted first. But this was a great success for the theory of gravity because it wasn't just using orbits; they were using individual sightings and observations to determine the orbit. And actually, this technique that Gauss developed, called basically using 3 points to determine an orbit, is used commonly by air defense and stuff like that for determining satellite orbits. Yes, question?
I was just wondering, at the time of the illustration there, did they have the mathematical tools to calculate the speed necessary?
Yes, actually, yes. Newton and others were developing the calculus at the time. And so they had the concept of derivatives and change in position with respect to time and change in velocity with respect to time. So a lot of the mathematical tools were being developed by these guys as they were going. In fact, it's really confusing to look at some of the older papers. We take for granted our modern mathematical notation on a lot of this stuff in terms of how much we abstract that behavior. These guys wrote it out, one vector component at a time. And some of the papers are really tough to go through. You wonder, did they write this, or did they have a secretary go and say, duplicate this equation and change this subscript? So anyway, a number of fascinating possibilities though started showing up. Alexis Bouvard in 1821 noticed some inconsistencies in the orbit of the planet Uranus. Now, they weren't quite sure what was causing these inconsistencies. there was some ideas that maybe Newton's law of gravity breaks down in this area far out from the center of from the sun. So maybe there's a possible difference in the theory of gravity. Or the other possibility was there was another object perturbing the planet. Frederick Bessel in 1844 discovered anomalies in what we call the proper motions of the stars, Sirius and Procyon. These are two fairly bright stars near the constellation Orion. They're both called the dog stars, as Sirius is in Canis Major and Procyon is in Canis Minor. And he would notice that the stars kind of moved in a little bit of a wobble, is what he measured. Now, most things, the assumption is that objects moving in a straight line will tend to stay in a straight line. But the other possibility was there was some other object perturbing it. And you might consider this as one of the first examples of what would become one of the first dark matter problems in astronomy, where we detected something by its gravity before we actually determined the underlying cause. Because in 1846, Leverrier and John Couch Adams discovered the planet Neptune based on Uranus's orbit. These guys, they weren't collaborators, they were competitors, and there was a lot of national honor tied up in this. In fact, Leverrier kind of lost out in this. Some people will talk about them both as the co-discoverers because they got it so close and they were in such tight competition. But Leverrier, felt that, they'd stolen Neptune from him. And so he went hunting for other anomalies in the solar system and discovers this anomalous perihelion shift of the planet Mercury, where its orbit seems to, the plane of its orbit seems to shift around in a way that cannot be accounted for by the known forces on it. Well, by 1862 and 1896, they discover what the problems were with the motion of the stars Sirius and Procyon. They find a little tiny faint star. They're barely detectable. Look how long it took between 1844, it took almost 20 years, and another, almost 50 years for them to make this determination, to solve that mystery.
Found it by observation?
Yes. Yeah. Alvin Clark actually was one of the guys that had done a lot of telescope construction. He was actually a fairly famous telescope builder. And he was building some of the largest refractors of the day. So they were always trying to make sure they could test these things out. So what finally happened? Well, by 1957 we could finally do the Newton's Cannonball experiment. By 1958 we were determining the astronomical unit by bouncing radar off Venus. Now think about how they were doing this. They weren't measuring the distance of the Earth from the Sun. They were saying, this is the distance to Venus. We know the relative distances of the Sun, from the Sun, of the Earth to the Sun, and Venus to the Sun. So if we can put an absolute value on the difference between these two, then we know the actual distance. So they determined this distance indirectly. We finally get a spacecraft to escape Earth's gravity, another prediction of Newton's law, that there would be a velocity at which point an object would leave and not be able to necessarily come back. And our first successful interplanetary mission, i.e. it went where they wanted and it was still working, by 1962, which was the first, they actually were able to use these measurements to navigate. And they were all done 220 years after the initial prediction with indirectly obtained distances, which were used, and they navigated with fairly good precision with them. So, for a theory that you couldn't do this key experiment for a very long time, they did pretty darn good with it. In fact, I've often been curious as to whether there's anyone in the 50s that maybe was arguing that, well, you can't prove that gravity applies, out there. Today, of course, we don't think about the value of satellites and space travel that much. We have them available for weather forecasting, communications, and of course exploration. But there's a little bit of you might think I pulled a little bit of a fast one on you there. Because I mentioned that gravity was measured in the lab back when we measured the value of G. That they did the torsion balance experiment and measured the forces and got a value of G from that. Well, not really. They sort of said, okay, Newton's law is right, and we move around the F and the G and stuff like that. We know the F, and we solve the equation for G. And so they assumed Newton's law was correct and just solved for g.